Hello everyone. When you look up at the night sky, sometimes you notice a steady bright dot moving across. That's not a shooting star, that's a satellite. Earth already has one natural satellite, the Moon, which completes one revolution in about 27.3 days. But since 1957, humans have launched thousands of artificial satellites for GPS, internet, weather forecasting, and even for live sports broadcasting. So the big question is, how do these satellites stay up there without falling back? The answer lies in Newton's law of gravitation and Kepler's laws. Let's explore the science behind this. Think of swinging a stone tied to a string in a circle. The string pulls inward, giving the centripetal force. For a satellite of mass m at a height h, the orbital radius is r sub e plus h. The centripetal force required is mv squared divided by r sub e plus h. But here there's no string. The pull comes from Earth's gravity itself, which is gmem divided by open bracket r sub e plus h close bracket squared. Equating these two gives us the condition for orbital speed. Earth's gravity acts like an invisible string keeping satellites in orbit. From this balance, orbital velocity comes out as v equals square root of gm e divided by r sub e plus h. If the satellite is very close to Earth's surface, where h is 0, this reduces to v equals square root of g r sub e. Notice something important. Orbital speed does not depend on the satellite's mass. Whether it is a tiny CubeSat the size of a shoebox or a massive space station, the required orbital speed at a given height is the same. Also, the farther you go from Earth, the slower the orbital speed. It's like outer space has fast lanes near Earth and slow cruising lanes farther out. Now let's find how long a satellite takes to complete one orbit. The distance for one revolution is 2 pi times r sub e plus h. Dividing this by orbital velocity gives the time period t. After substitution, we arrive at t squared equals 4 pi squared divided by gm e multiplied by r sub e plus h cubed. This is exactly Kepler's third law. The square of the time period is proportional to the cube of the orbital radius. The same law that governs planets around the Sun applies to satellites around Earth too.
Now let's zoom into satellites that are close to Earth, called low Earth orbit satellites. For heights much smaller than Earth's radius, the formula simplifies to t equals 2 pi times the square root of r sub e divided by g. Numerically, this comes to about 85 minutes. That means a low Earth orbit satellite goes around Earth roughly 16 times in a single day. These satellites are used for imaging, weather monitoring, and defense. They are always busy, circling the planet over and over, giving us constant data. Here's a powerful application. Astronomers often use satellites to calculate planetary masses. Take Mars and its moon Phobos. Phobos orbits at a radius of about 9.4 times 10 to the power 3 kilometers with a period of 7 hours and 39 minutes. Using the formula t squared equals 4 pi squared divided by gm times r cubed, we can solve for the mass of Mars. Substituting the values, the mass comes out to about 6.5 times 10 to the power 23 kilograms. So we don't weigh planets on giant scales. Instead, we observe their satellites and let physics do the rest. Let's wrap this up. Satellites are held in orbit by the balance between Earth's gravity and the centripetal force needed for circular motion. The orbital velocity is v equals square root of gme divided by re plus h, and the orbital period follows Kepler's law. T squared is proportional to orbital radius cubed. Low Earth orbit satellites take about 85 minutes to complete one revolution, while geostationary satellites high above Earth take exactly 24 hours, staying fixed above the same spot. From GPS and weather forecasting to communication and planetary science, satellites are the backbone of modern technology. So next time you check directions on your phone or watch live cricket streaming, remember, a tiny satellite silently obeying Newton's laws, made it possible. That's the beauty of physics. See you in the next class with another exciting journey into the universe.